Hello everyone. Today let's solve the problem number 74. Search a 2D matrix. So you can just go through the question and you can go through the example as well to understand the question pretty well. So I'll just summarize the question so that it will be easier to understand. So what the question states here, we are given an m into n matrix with the following properties. So what's the first property? Each row is sorted in non-decreasing order. So you can clearly see here, each row is sorted in non-decreasing order. So you can see here, right? 1 followed by this one 3, followed by 5 and followed by 7. Each row is sorted in non-decreasing order. So that's what they have mentioned here. The second condition is here, the first integer of each row is greater than the last integer of the previous row, right? So yeah, obviously, right? Here you can clearly see the first integer of the each row is greater than the last integer of the every previous row. You can clearly see here 10 is greater than 7 and here 23 is greater than 20, right? So then what is our task? Mainly our task is to determine if a given target integer exists in the matrix or not. If it exists, then we have to return true. If it doesn't, otherwise we have to return false, right? So this is our this is our main task. Our task is to determine if the given target integer exists in the matrix or not. If it exists, then we should return true. If it doesn't exist, then we have to return false. So initially, you can clearly see here. Just give me a second here. So you can clearly see here, target they have given 3 and the target is found in the matrix here. You can clearly see this one, right? The second element in the first row. So we are returning true here. Here they have given target 13 and 13 is not present in the matrix, so we are returning false. This is fine. So let's discuss the approach and then let's discuss the edge cases one by one and then let's write the code and discuss the complexity of the code that we have written. Initially, let's start with the approach. So here let's discuss the approach step by step. Let me give here approach. So the first thing that we have to keep in mind here is we are going with the approach binary search. So we'll be making use of the binary search here. So this we have to keep in mind. So first step here is we have to understand the flattened matrix concept. So here, since the matrix is row sorted and column sorted, we know that the matrix is row sorted and column separated. That's what they have given in the question, right? So the matrix is row sorted and column separated. We can imagine the matrix as a single one-dimensional sorted array. So suppose if I consider this example, let me consider this example 1, 3, 5. This one followed by 7, 10, some number, random number I am giving. This has to be sorted, right? So this is fine. This can be viewed as within the single this one array. We can give like this 1, 3, 5, 7, 10, 12. So this is the concept of flattened matrix, right? So this is first step and let's move on with the second step, nothing but the binary search. So as I have said, we will be making use of the approach binary search, right? Let's see. So first step here is we have to treat the matrix as one-dimensional sorted array with the indices ranging from 0 to indices start from 0 to m into n minus 1. Why here m into n minus 1? Because m, we are considering rows and columns, right? Here m is nothing but rows and n is nothing but columns. Nothing but this is length minus 1, the last index we are considering, m into n minus 1. So this is the first step. We have to treat the matrix as one-dimensional sorted array with the indices ranging from 0 to m into n minus 1. This is first step. Second step is we have to use the binary search to find we are making use of the binary search to find the target. We are making use of the binary search. So let me come here. So as we are making use of the binary search to find the target, first what we will do, first step is here, we have to calculate the middle index mid. This is the first step. We are calculating the middle index mid, and we are mapping the 1D index mid back to the 2D indices. How can we map the one? We are considering 1D index, right? Through the flattened this one matrix concept. Then we have to map the 1D index mid back to the 2D indices. We can just make use of here row equals math.floor we can make use of, or we can just make use of double tilde operator, right? So mid by n here. You can just make use of it. This one is nothing but row number here. This is just for the reference, just for the understanding purpose. And this is for the row. And for the column, it is mid module n, right? So for the row, it is math.floor of mid by n. This is nothing but the row number. This is nothing but the column number, right? Then let's come to the main part. We'll be making use of the this one. We will compare the value at matrix of row and column. We will be comparing the value at matrix of row and column, right? So with the target, so we'll be comparing the value at matrix of row column with the target. If the value, this is simple, right? This is pure binary search. So if the value matches, then if value matches, then we will return true. This is first thing. If the value is smaller than target, value smaller than target, then what we will do? We will move the left pointer to mid plus 1. I'll just give here L equals mid plus 1. What about when the value is greater than target? Then if the value is greater than target, then we will move the right pointer to mid minus 1. So what we are doing here, these three steps, this is important, right? So we are comparing the value at matrix of row and column here. We can with the target, we can clearly see here. Then if the value matches, then we are returning true. If the value is lesser than target, then we are moving the left pointer to mid plus 1. Then if the value is greater than target, we are moving the right pointer to mid plus 1. So this is the approach that we will be going with. So right, we'll be making use of the binary search, and we should be knowing the this one flattened matrix concept as well along with the binary search. I hope the approach is completely clear. Next, let's discuss the edge case one by one and then write the code and discuss the complexity of the code. So let's discuss the edge cases one by one. I'll just come here. Let me give edge cases here. The first edge case here we are considering is matrix with one element. So I'll just consider here, I'll just give input matrix 5, right? This is fine. Let me consider target as 5 as well. So here a single element matrix should return true if the target matches the element, and target is matching the element. So we have to return true here. The output will be true here. This is for the condition matrix with one element. One element. Let's move on with the next edge case. Nothing but we are going for the edge case target less than all elements. So target less than all elements means I'll just consider this one matrix. Within this one, let me consider 10, 20. Yeah, this is fine. And target, let me consider target less than all the elements, right? Let me consider target 5 or 6, anything less than 10 here. 10 is the least element here. So we are considering 5 here. So if the target is smaller than the smallest element present here, if the target is smaller than the smallest element, then we are returning false. Here the output has to be false. The element is not present here in the array at all, right? So you can clearly see here. So this is for the condition target less than all elements. This is fine. This is the second edge case. Let's move on with the third edge case. Third edge case is nothing but target greater than all the elements. So I'll just consider, previously we considered target less than all elements. Now we are considering target greater than all the elements. I'll just consider here the same one. Let me consider 10, 20, and let me consider target as 30 here. So let me consider the target 30 here. If the target is larger than the largest element, you can clearly see here the largest element is 20. If the target is larger than the largest element, then the output will be obviously false, right? So this is for the condition target greater than all elements. So let's move on with the next edge case. Nothing but target in the first position. So I'll just consider this one matrix. So here let me give 1, 3, 5, and let me consider one more array. This one nested array. This one will be 7, 9, 11. Anything you can consider. So I'll just give here target. Target at the first element we are considering. So target, let me consider 1. This has to be true. Quite obviously, we are finding the element in the and here within the matrix, right? Within this array. So the output will be, if the target is the smallest element or the first element, then the output will be true here. This is for the condition target in the first position. This is fine. This is for the fourth edge case. Then let's move on with the fifth edge case. Nothing but target in the last position. Target in the last position we are considering, right? So I'll just consider here same example 1, 3, 5, 7, 9, 11 I considered, right? So this is fine. So target will be 11. Let's consider target as 11 here. So the output here will be true. If the target is the largest element, nothing but the last element, you can clearly see here, nothing but the 11, then we have to return true. Then the output will be true here. So this is for the condition target in the last position. This is fine. So we have discussed all the edge cases. So first one was for matrix with one element. Second one was for target less than all the elements. Third one was for target greater than all the elements. Fourth one was for target in the first position. And final one is for the target in the last position. So I hope all the edge cases are clear. So let's start writing the code. I'll explain the code while writing the code itself. Then let's discuss the complexity of the code that we have written. So let's start writing the code. First step, as we had discussed in the approach, let's determine the dimensions of the matrix. So I just give here, let m equals length of the matrix and n equals, m is here, I'm considering m as this one rows and n as columns, right? N I'll just give here matrix of 0 dot length. So this is fine. Next step is we have to initialize the binary search pointers as well. So left starts at the 0 as usual and the right starts at the last index. Nothing but we had discussed that one, m into n minus 1. So I'll just give here, let l equals 0 and right starts from m into n minus 1. So the third step, this is the main step. We have to perform the binary search. First thing is while left less than or equal to right, then only we can move forward. So we have to calculate the middle index first. So I'll just consider mid here. Mid will be, instead of math.floor, I just consider double tilde operator. This will be left plus right by 2. This is fine. So after calculating the middle element, middle index, then we have to map the one-dimensional index back to the two-dimensional row and column. We had discussed this one already. So how can I write this? I'll just give here val equals matrix of, instead of math.for, let me consider double tilde operator. I had written during the approach this one, mid by n. And so get the value, we are just getting the value at the matrix of row and column. Another thing is mid module n, if you remember. So did I miss something here? No? What did I miss here? By twice I considered here bracket. So let me remove this one. This is fine. So the final step is we have to compare the value with the target. Nothing but we had discussed the three things. One is if the target is found, nothing but if value equals target, we can just return true. If the value is less than target, then we can just move the left pointer forward, and if the value is greater than the target, then we will move the right pointer backwards, right? If this is simple, I'll just give here value target, then let's return true. Then if value less than target, then left pointer, we have to move the left pointer forward, right? Sorry, this has to be mid, I have considered, right? Variable net, yeah. Mid plus 1, and the final one is if the value is greater than target, then we will move the right pointer backwards. I'll just give here else r equals right equals mid plus, this has to be mid minus 1, right? Yeah, this is fine. So the final step is if the target is not found, we have to return false. So we have seen this one in the edge case while discussing the approach as well. So I'll just give here return false. So let me format this one once and let me hit the run. So you can clearly see the sample test cases are getting passed here. So let me hit the submit button now. So I can clearly see all the test cases are getting passed here. The code is getting accepted. So the code works absolutely correct. So here, let's quickly discuss the time complexity and the space complexity of the code that we. So you can clearly see the approach that we went with here is the binary search. And the overall time complexity here would be big O of logarithmic m into n. As we are dealing with the matrix, we have rows and columns, right? So it's a big O of log of m into n. So binary search on m into, we are performing binary search on m into n elements, right? So overall, this one time complexity would be big O of logarithmic m into n. And what will be the space complexity here? Space complexity would be big O of 1 here. Why the space complexity here is big O of 1, not the big O of n? Because we are not making use of any extra space, right? Except a few variables. So the overall space complexity would be here big O of 1. So yeah, I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.